Bismillahirrahmanirrahim. This is a class of group theory and method of chemistry, and today's point of discussion is the point group. In this lecture we will discuss about the groups. What is a group? The molecular symmetry group and the point groups, and assigning of the point groups to some simple molecules, and classification of the point group, recognition of the features for the common point groups, and scheme used for assigning the point groups to simple molecules. At the end, I will give you a video link for practice on simple molecules. So first of all, what is a group? A group must possess some defining properties. Here I am giving you 4 defining properties that should be present in a group. The first one is the closure. Closure means that the product of any two elements present in a group and the square of each element must be present in a group. For example, if we have A and B elements in a group G, the multiplicity of these two elements, multiplicity product of these two elements C should also be present in the group. The second property is the associativity. Associativity means that if one element in a group must commute with all other elements and leave them unchanged. For example, we have A, B and C elements. The product of AB multiplied by C should be equal to the product of BC multiplied by A. Another property is identity. Identity is represented by E, and it's rotating a molecule by an angle of 360, which leaves the molecule unchanged. Identity is an element which is like doing nothing to the molecule. Although we rotate the molecule by an angle of 360, but it seems that nothing have been happened. If we multiply identity with any element of the group, it should leave the element unchanged. The fourth property is the inverses. The associative law of multiplication must hold. That is, every element must have a reciprocal, which is also an element of the group. For example, we have an element A which is present in a group G. It must have a reciprocal A inverse. The A inverse should also be a member of G, and it should satisfy the law that the product of A and A inverse is equal to the product of A inverse and A, which both are equal to the identity E. So we can write that A inverse is B. If A is a member of group G, then B should also be a member of G, and it will satisfy this law that the product of A and A inverse is equal to the product of A inverse and A, which is equal to the E. So any group must possess all these 4 properties. Now we are coming towards the point group. What is the point group in the group theory? A point group describes all the symmetry operations that can be performed on a molecule and that result in a conformation indistinguishable from the original conformation. It means that if we look at the molecule, that how it looks like, and then we apply some symmetry elements, but after applying this symmetry element, the molecule appears as it was. So there is no change in the molecule after applying the symmetry element. If there appears a change in a molecule after applying a symmetry element, it means that the symmetry element is not present. Point groups are used in the group theory for mathematical analysis and to determine the properties of molecules, molecular orbital. Molecules with the same symmetry elements are usually placed in the same group, point group. The point group are helping us in identifying many properties. If the molecule are present in the same point group, it means that they will have the same vibrational spectra, and they will have the same structure. Now, before assigning a point group to the molecule, we have to do some observations. First, we inspect the molecule and make a complete list of symmetry elements that are present in the molecule, followed by complete list of the symmetry operation generated by each molecule. When we recognize the list of the symmetry element present in a molecule, we observe that if it is satisfying all the criteria of the 4 criteria of the mathematical groups, which I have told you in the previous slide. The properties, that is closure, associativity, identity, it must possess all the 4 properties which we discussed earlier. And then we recognize that all the molecules having the same list of symmetry element belong to the same point group. Now we are coming towards the description of the point groups. Symmetric point groups have been divided into 5 classes, which are summarized below: the non-axial groups, cyclic groups, dihedral groups, polyhedral groups, and the linear group. First of all, the non-axial group. The non-axial groups are highly unsymmetrical groups, that is the C1, CS, and Ci. C1 possesses only identity, while the CS possesses identity as well as horizontal mirror plane, and the Ci possesses center of inversion in addition to the identity E. So it is possessing only very few symmetry elements in addition to the E. The example of the first one, C1 point group, is fluorochlorobromomethane, which is highly unsymmetrical molecule and possess only identity. While the CS and C2, they are also unsymmetrical molecules, but they possess 2 other symmetry elements in addition to the identity. Then we come towards cyclic group. The cyclic groups, although they are not very highly symmetrical, but they possess few symmetry elements other than the identity. The first cyclic group is CN, second one CNV, third is CNH, and the fourth one is SN. The first one, CN, it possesses rotation axis CN as well as the identity. For example, if we have dichloroethane, it possesses the C2 rotation axis in addition to the identity, and CNV groups, they possess rotation axis as well as vertical mirror plane. Example of it is ammonia, and the CNH possesses horizontal mirror plane and improper axis of rotation as well as rotation axis and identity. Example is BF3. Although the ammonia and trifluoroborane, they look quite similar in their molecular formula, but if you look at the structure is quite different. Ammonia is a pyramidal, while BF3 is a trigonal planar molecule. So although their formula, they look quite similar formula wise, but they are placed in different classes of the in different classes as their structure is quite different. So will be their behavior in the vibrational spectrum. And then is the SN, which is possesses identity as well as the improper axis of rotation. We will discuss about the examples a bit later in the next slides. And then are the dihedral groups. The dihedral groups are more symmetrical than the cyclic groups. They possesses rotation axis and sometimes they possesses C2 rotation axis in addition to the principal axis. The first group is DN, the second is DNH, D and D. The D group is possessing identity as well as the rotation axis, and it can possess few C2 axes as well. While the DNH group is possessing rotation axis, horizontal plane, and also C2 rotation axes are present. Example of this is benzene. In benzene we have C6 as a principal axis, but but it possesses 6 C2 in addition to the principal axis and also 3 C2s. As well as it possesses the horizontal planes, dihedral plane, and the vertical plane. The D and D group possesses the rotation axis, C2 axis, as well as the dihedral plane. Example is ethane. We can also pick other examples, but the structure of the molecule should be similar to these one. For example, if we pick any other example, but the structure should be like benzene. And then we come towards the polyhedral or the cubic groups. The cubic groups are more symmetrical point groups. They possess quite a good number of the symmetry element present in them. First one is the tetrahedral group, second is the octahedral, and then we have the icosahedral. The tetrahedral group is possessing symmetry elements E, rotation axis C2, and C3 rotation axis, improper axis of rotation is 4, and the dihedral plane. It I have selected here the example of tetrachlorocarbon, but any molecule which is possessing tetrahedral structure, whether it is simple molecule or it is a complex, but if it is possessing a tetrahedral structure, it will possess all these symmetry element, and it will be placed in the tetrahedral. Same is the case with the octahedral. The octahedral, I have taken here the example of SF6, but any molecule or any complex which is possessing octahedral structure will have all these symmetry element present in it, and the class will be the octahedral point group. Also, the icosahedral, we come across the tetrahedral and octahedral molecule, and very few icosahedral molecule, but still if we have an icosahedral molecule or complex, it will possess all these symmetry elements. The last class is the class of the linear molecules. In the linear molecules, we have the two classes, C infinity V and D infinity H. The infinity H because the linear molecule possesses an infinite axis of rotation. In the C infinity V group, we have identity C infinity rotation axis, and the sigma V, which is a vertical plane. Example of it is, I have taken it hydrochloric acid. It can be any heteroatomic molecule which is having a linear shape. The D infinity H possessing rotation axis, an infinite rotation axis, sigma V, sigma H, and also center of inversion, and maybe it possesses C2. Example I have taken here is oxygen, but any homoatomic molecule can be placed in this group. Now we come towards discussion about these different groups with the examples. I am putting the structure of these molecules as well, but if you are looking at the structure as I have told you in the class, and we have made some models, although I don't have the models available here, but you can make something like that, like those models for yourself, and you do practice on the symmetry elements. For example, if we take the C1 class, we have this example of chlorofluorobromoethane. It possesses only identity. If you make this molecule from a model and try different symmetry elements, you will find that we have only the identity element E. Now look at the CS group. I have taken the example of thionyl chloride here. It is possessing identity as well as the sigma H. You can easily recognize the sigma H, which is passing in between the both chlorine and cutting the sulfur and the oxygen. In the CI group, I have taken this example of chlorodiafluoroethane. You can easily see that these atoms can exchange their position passing through the center. For example, this chlorine can exchange its position with the other. This chlorine can exchange its position with the other chlorine passing through the this is the center, passing through the center. Also, the fluorine can exchange its position with the other fluorine passing through the center, and same is the case with the hydrogen. And also these two molecules, these two carbons can also exchange their position passing through the center. So it is possessing center of inversion in addition to the identity. Is placed in the class CI. Now if we look at the point group of water and ammonia, although formula, if you look at the formula of water and ammonia is quite different. It's triatomic and it's tetratomic, but if you look at the structure or the symmetry of the molecule, they are quite similar. This is the molecule of water. It is possessing a center a rotation axis C2, which is passing through the oxygen, and also it possesses two vertical planes. One of the vertical planes, sigma V, this is in the plane of the molecule, which means that it's passing through all the three atoms, cutting all the three atoms in equal halves, while the other symmetry, the vertical plane, sigma V prime, it's passing through the oxygen, it's cutting the oxygen and passing in between the two hydrogen. So we have the C2 rotation axis and sigma V and sigma V prime in the water molecule. It's placed in the class C in V, which is this so as its rotation axis is C2, so its class will be C2V. Ammonia is also placed in the same class C and V, but as the ammonia is having C3 axis of rotation, so its point group will be C3V. Ammonia is possessing C3 rotation axis and also 3 sigma planes. Each sigma plane is passing through one of the oxygen, and one of the hydrogen. So we have 3 vertical planes in the ammonia. Ammonia will possess the point group C3V. So we can see that water and ammonia, although they are quite different from the formula, but they are placed in the same class, and they have very little difference in their point group. Water is having the point group C2V, while ammonia is having its point group as C3V. If you now the highly symmetrical groups are the QV groups, which are the tetrahedra and the octahedra. They are highly symmetrical groups, and they are possessing quite good number of the symmetry elements. Any molecule or any complex which is possessing tetrahedral structure will be placed in this class. Sometimes we come across the distorted shapes, distorted octahedral shapes. For example, if we have this octahedral molecule, it is having 4 ligands as X and 2 ligands as Y. So the distance, the bond length of the Y can either be elongated or shortened depending upon which type of ligand these are. Sometimes we come across these distorted groups, although they are having D and H groups. They have horizontal plane in addition to the vertical planes. Many inorganic complexes belong to this class of symmetry. Now, when we are assigning the point groups to the molecule, we typically ignore some commonly we ignore some fine details such as conformation isomers of the ligands, etc. In working problem with the group theory, the point group of the elements will usually be provided to people. In general, we need not to assign molecule to its point group. Recognition of the common features are useful. Now, how we recognize the common features? Some schemes are developed for this to recognize the common feature. Now look at this scheme. First we look at the molecule and see if it is a group of low symmetry. If yes, then it can be either C1, CS, and or CI. We can distinguish among these three by looking at the symmetry elements. If the molecule is not possessing to the group of low symmetry, we look at if it is belonging to the group of high symmetry, that is tetrahedral, octahedral, icosahedral, either the linear groups. If yes, we can further distinguish to which class the molecule is belonging. If it's not belonging to this group, we look at the highest order of rotation axis, Cn. If the Cn or the principal axis is perpendicular with the C2, then it will belong to the D group. If it's not perpendicular, it will belong to either C or S group. If it's belonging to the D group, we look at the octahedral plane. If the horizontal plane. If the horizontal plane is present, then it is D and H. If the horizontal plane is missing, we look at the dihedral plane. If the dihedral plane is present, it will belong to D and D class. If it's missing, then it will belong to the DN. On the other hand, if the molecule is belonging to C or S group, we look at the horizontal plane. If the horizontal mirror plane is present, yes, it will belong to C and H. If no, we look at the vertical plane. If the vertical plane is there, it belongs to the C and V. If the vertical plane is also missing, we look at the improper axis of rotation. If the improper axis of rotation is there, it will belong to S2N groups. If it's missing, it will belong to the CN group. Now we look at the simple example of the carbon dioxide. carbon dioxide is a linear molecule, so we start with the recognition if it's a is it belonging to special group? Yes. Is it belonging to the linear group? Yes. So we look at if center of inversion is present. Of course, it is having two oxygen on both sides of the carbon. The oxygen can exchange their position passing through the center. So the center of inversion is present, it will belong to D infinity H. Here I am giving you another scheme for the same purpose assigning the point group to the molecule. Some people prefer to use the previous scheme as I have shown, and some people prefer this one. Both the schemes are simple. You can easily follow any of these. Look at the molecule. If the molecule is linear, yes, then look at the center of inversion. If the center of inversion is there, the molecule will belong to the D infinity H class. If the center of inversion is missing, molecule will belong to C infinity V class. Now, if the molecule is non-linear, we look at the condition. If there are more than 2 Cn, the rotation axis should be greater than C2. If yes, we look at the center of inversion. If the center of inversion is there, we look at C5. If C5 is there, it's icosahedral. If the C5 is missing, it is the octahedral. And if the center of inversion is present, it is the tetrahedral. The center of inversion is present in the octahedral and icosahedral groups, but it's not present in the tetrahedral group. Now, if this condition is not present, then we will look at the principal axis. If the principal axis is there, we look at this condition, select the principal axis, and then we look if there is any C2 axis perpendicular to the principal axis. If this condition is present, it will belong to the cubic groups. Then we will look at the sigma H. If the sigma H is there, it will belong to D infinity H. If the sigma H is missing, we will look at the dihedral plane. If the dihedral plane is there, it will belong to the D and D class. If it is missing, it will belong to the DN. If this condition doesn't exist, the answer is no. We look at the sigma H, which is the horizontal plane. If it's there, it will belong to C and H. If it's missing, we look at the vertical plane. If it's there, it is the C and V. If it's missing, we look at the rotation, improper axis of rotation. If the improper axis of rotation is present, the molecule will belong to the S2N class. If not, then the molecule will belong to the CN class. Now, if this principal axis, rotation axis, is not present, we will look at the sigma. If the principal rotation, if this rotation axis is missing, it means that they are belonging to the highly unsymmetrical class, that is the axial, non-axial groups. We look at the sigma. If the sigma, that is the mirror plane, if the mirror plane is there, it will belong to CS. If the mirror plane is missing, we look at the center of inversion. If the center of inversion is there, it is the CI class. And if center of inversion is also missing, it will belong to C1. This is the class which is possessing only identity. You can follow this link in this video. There is this video is for practice on simple molecule. Somebody also given this video on the YouTube, and they are assigning the point group to simple molecule. It can be useful for you people. Please try this one as well. In the next lecture we will continue with the further example. Thank you.